Hello, this is the short lecture given to illustrate Sobolev inequalities. In the past, we've been working so hard on all those properties of Sobolev spaces, WPP, like its approximation and extensions. We are not doing this for fun actually, we expect some applications. In PDE theoretical research, we wonder if a sort of space like, for starters, W1P can be embedded into other familiar spaces. In other words, if a function U belongs to W1P, does it automatically belong to other spaces? It is clear by definition that W1P can be embedded into W1 and LP, but we are not satisfied with these trivial results. But inspired by this, which inspires us, that can we convert some of this differentiability into integrability, or by contrast, can we convert some of this integrability into differentiability? Although this differentiability is not classical, it's weak derivatives. We only have weak derivatives, but we also fancy something like this. So the answer is yes, and although in different conditions. So we introduce our main theorem for today. Let omega be a boundary open subset of Rn, and C is a positive integer. Then W1P omega can be embedded into LQ omega, where P is larger than or equal to 1 and smaller than n, and C mu gamma omega, where P is larger than n and smaller or equal than positive infinity. So this Q actually is not arbitrary, it's to be set. And here's the deal. We're gonna find this proper Q and we're gonna prove this theorem. Firstly, let's find Q. That means if something like this holds, what this Q is going to be. This is not going to be arbitrary, and actually it has a specific form. Let's see this again. What does this mean? W1P omega can be embedded into LQ omega. That means for any U in W1P omega, U belongs to LQ omega, and we estimate that U, the norm of LQ omega, is less than or equal to some C times U, the norm of W1P omega. By definition, this norm of W1P omega has two parts, that is U, the norm of P, plus EU, the norm of P. So the key is to estimate something like this. LQ omega is less than or equal to some C times u du LC omega. For convenience, we enlarge the area from omega to the whole Rn. And also we enlarge the functional space from W1C omega to single 1 omega temporarily for convenience. We are going to find the proper Q under this circumstance. So let's calculate this. This is Rn. We take a U, before this we take a U in single 1 Rn. We take a U from single 1 Rn and take U lambda, defined as U of lambda x. We insert this U lambda into this inequality. We have Rn U lambda x, the power of Q dx, the power of 1 over Q is less than or equal to some C times, let's say du lambda is lambda times du of lambda x. That is lambda Rn du lambda x, the power of C dx. Here's a lambda out, and the power of P, and then the power of 1 over P. So there's only a single lambda out with the power of 1. And then we take P is lambda x. We have Rn ut, the power of Q dt. And there's a lambda, the power of n out. And there's a 1 over Q. So the index is 1 over lambda, the power of n over Q is less than or equal to. Similarly, the right side is lambda, copy this, Rn dut, power of P dx, power of 1 over P. There's a lambda, the power of n out. And there's a 1 over P, so n over P. Now this is a LP norm. This is a LP norm. So we write the inequality as the norm of LP we get, and then time this lambda to the right side. We have U, the norm of LQ, Rn is less than or equal to some C times lambda 1 minus n over P plus n over Q times du LP Rn. So since U belongs to single 1 Rn, it also this equation is also proper to this U. So this index on the shoulder of lambda, this should be 0. We have 1 minus n over P plus n over Q is 0. Or otherwise, we can take U is non-zero because we only have to find one U. We take this kind of U. It's non-zero U and go for the process. And then, if this is not 0, we let lemma goes to 0 or infinity. We will reach a contradiction since both u and du are non-zero. So we got an equation of q. We solve it, we get q is np over n minus p. So this q is not arbitrary, it has a specific form, np over n minus p. So this q is np over n minus p. Now let's prove this theorem. Before prove it, let's write a famous lemma, which is the key step to prove this theorem. Very famous lemma. For any u belongs to semi-1 Rn. Again, for convenience, we enlarge the area to whole Rn, and we put some more conditions on the function u in semi-1 Rn, and p is larger than 1, larger or equal to 1, and smaller than n. So we have, and then u, the norm of error qRn is less than or equal to some c times du, the norm of error pRn, where q is this, np over n minus p, and c only depends on n and p. Notice that before we prove it, notice that u, the compactness of u is essential, because otherwise we take u is 1. So we will reach an contradiction. This is going to 0. Going to be 0. So this compactness is essential to this lemma. Now we prove it. Firstly, we assume that p is 1. Hence, q is n over n minus 1. So we are going to calculate something like this. Rn u, the power of q, is n over n minus 1. dx, the power of n minus 1 over n. But, and the right side would be something similar to du, the power of p, something like this. To combine this u and du together, it occurs us that we can apply Newton-Leibniz equation. We have ux is from negative infinity to xi, d x1 yi xn. There's xi minus 1, is xi plus 1. dyi is Newton-Leibniz. And for here, this holds for any I from 1 to n. And we have n fractions like this. We time them together. We have to we enlarge the internal to whole R and put an absolute on it. D U x1 yi xn dyi. So there are n terms. We find them together. I from 1 to n. The first one, x1, x2, x3, we time them together. So we divide this with n over n minus 1, n minus 1. It's natural for us to consider this, to integrate the left side on whole Rn and integrate the right side on the whole Rn. But we notice that there are n fractions, n integrals in the right side, and the index is only 1 over n minus 1. So if we integrate this in the whole Rn, it's hard for us to apply this holder inequality to have a further estimate. So we won't integrate it in the whole Rn. We have to eliminate some of this fraction. We have to eliminate one of these fraction out to use this holder inequality naturally. So we integrate it with respect to only x1. We have the left side is ux n over n minus 1 dx1 is less than or equal to. Notice that among these n fractions, there is one fraction that has nothing to do with x1. Which one? The first one, when I is 1. The x1 has been integrated, so we extract it out. That is dux dy1. The first one has nothing to do with x1 times the remaining part has n minus 1 integrals, and this index is 1 over n minus 1. So we can apply the holder's inequality naturally. We have pi from 2 to n d 1 to d ux d say x1 y I dx1, the parabola n over minus 1. There's also a parabola n over n minus 1. So this is the first step. We don't integrate it in the whole Rn. We integrate it with respect to only x1. And the next step, similarly, we integrate it with respect to x2. Our final goal is to integrate it in the whole Rn. So one by one, we have 1, 2 ux, the parabola n over n minus 1 dx1 dx2, this is left side, less than or equal to. Notice, again, there's also one fraction that has nothing to do with x2. Which one? The second one, when is 2. Since the x2 has been integrated, so it's extracted out 1, 2, dux. dy2, x2 has been integrated, dx1 power 1 over n minus 1 times the remaining part as again n minus 1 fractions. This is 1 over n minus 1. Then by Holder's inequality, we have this 1 dy1 dx2 times I from 3 to n 1, 2, 3 du dyi dx2 dx1. So again, we can integrate it from x3 respect to x3 to xn. We can integrate every step. We have one fraction that has nothing to do with the corresponding xi. So finally, we get the left side would be Rn ux, the power of n over n minus 1 dx. Left side. Right side is going to be, eventually it's going to be pi from 1 to n, 1, 2, to n. There are n integrals. du dx1 dyi dxn. The power of 1 over n minus 1. So these n integrals are all the same. So it's hard for us to write an equivalent here. All those are less than or equal to. It's Rn du dx, the power of n over n minus 1. So we take this n over n minus 1 over n and n minus 1 over n. Eventually, we get this is u, the norm of error n over n minus 1 norm. So this is error q. Rn is less than or equal to, actually this is 1, but we take a save here, times this is du L1 norm. L1, this is P is 1. So we have proven that this lemma holds when P is 1. So now let's assume that P is larger than 1 and smaller than n. We'll apply the results that we have already proven that P is one case. So it's going to calculate something like Rn ux. The power of the cube this time is np over n minus p dx less than or equal to some c times the right side is going to be something with du. We have to find the proper index. Then we apply the results of P is one case. So it's hard. Yeah, it's hard to find the proper index in the first place. So we are clever people. We don't stick on it. We can use this. Apply. P is one case to function u, the power of gamma. Yeah, we don't know how to choose this gamma at the first place, so we use gamma, where gamma is to be selected. We're going to select a proper gamma to finish our proof. So that is Rn u, the power of gamma, the power of q. When P is 1, so it's n over n minus 1 dx, n minus 1 over n is less than or equal to some c. We know this is 1, but we take this c. Rn. So this du gamma, du gamma is gamma, u gamma minus 1 du. So this is, there is a gamma and u power of gamma minus 1 du. P is 1, so this is 1 and the power of 1 over 1. So we are going to convert the right side to this form. So we use Holder's inequality again. We got the second part is Rn du. We hope there is a P here. dx, the power of 1 over P. So the first fraction is going to be Rn u, the power of gamma minus 1, the power of P prime. P prime is P over P minus 1 dx, the power of P minus 1 over P. So there's inequality. And we'd like to combine these two fractions together. So we need this index is equivalent to this index. So we got gamma n over n minus 1 is gamma minus 1 times P over P minus 1. Then we can solve this gamma to be, I will copy the result, is P n minus 1 over n minus P. So the gamma which was to be selected is actually this. take this and insert this gamma into this inequality, and so that we can combine this to the left, and we calculate this n minus 1 over n minus p minus 1 over p. We can find, oh, that is q. You can check if you don't believe it. And this is 1 over q. And this index is actually q. You put this into there to check it. So the left side would be u, the norm of error q Rn is less or equal to c gamma. This gamma can be absorbed into this c. So c times du Lc Rn. So here is our conclusion of this lemma. Alright, we can use this lemma to prove our main theorem, the case 1. Actually, so proof of theorem 1. Let's see how much let's see the difference between the lemma, this form, and this form. This is u, the norm of error q omega is less than or equal to some c times u w1p omega. So the left part, this is Rn, this is omega, a boundary open subset of Rn. And the right side, this is only du, and there are W1p norms as both u, p, and u, the norm of p, and du, the norm of p. To deal with the area difference, we can use extension theorem. And to deal with this functional space difference, that u here is W1p and here is C01, we can use approximation theorem. So we are going to prove it. So firstly, by extension, for any u at in W1p omega, by extension theorem, we have u bar in W1p whole Rn, such that firstly u bar is u in omega, secondly u bar as contact support, and thirdly the norm of u bar in W1p Rn is less than or equal to some c times u, the norm of W1p omega. Since this u bar is in W1p Rn, by approximation here there are un in single infinity Rn such that un converge to u bar in W1P Rn. Since for any n L that is positive integer, we have un minus ul. Let's see. This W1P norm has both PDE consists of LP norm, LP norm plus DU LP norm. So, by this lemma, we have this lemma. Un minus ul, the norm of LQRn, is less than or equal to some C times DUN minus DUL LPRn. So since this converge in whole W1PRn, so this goes to 0 as NL goes to positive infinity. This holds due to both un and ul are in single one Rn. So since LQ space is complete, we get un converge to u bar in LQ space. And what's more, by this lemma, we also have for any n that is a positive integer, un, the norm of LQ is less than or equal to some C times DUN LP Rn. As this is called 4, this is called 5. This is called 6. This is called 7. Let's see whether it's enough for us to make an estimate. Now we put the left side here and the right side here. Right side LPRn. We are going to show that this is less than or equal to, less than or equal to, less than or equal to C times du LPRn norm. So firstly, from it's W1P norm. For this is W1P omega. Finally equal to omega. We start from the right side. By this, we have C times U bar W1P Rn. And since this W1P norm has both LP norm and So it's larger than or equal to, we have this. So we going to use this C times U bar, the norm of LP du the LP Rn. Because the U bar term has been eliminated. And this is by definition. Definition of norm of W1P. And it is larger than or equal to, we have LP, let's say, from here, from 5, we can reach a conclusion that DUM converge to DU bar in LP Rn. So we can larger than or equal to C times DUM LP Rn. And this by equation 7, inequality 7, we have larger than or equal to C times UM, the norm of LQ Rn. And this by 6, we have larger than or equal to C U bar LQ Rn. And this, finally, why does this is less than or equal to this? Because we have U bar is U in omega. So the left part of the U bar in Rn eliminate omega. Is actually this is positive, so this integral is larger than this. This is natural. We have to find is due to the first line. So we estimate this by the first line. We get this, and goes here. We got the final result. So finally, we prove this theorem of case 1. And case 2 is another beautiful story. I hope I got a chance in the future to record it for another lesson. Thanks for watching.